Over the past few videos, we have discovered Taylor-Maclaurin series for well-known functions like sin x, cos x, e to the x, etc. What we can actually do with those known series is create new, more complex series through things such as substitution, multiplying and dividing known series to create new ones, even integration and differentiation. And so we're going to do some examples of that. The thing you need to keep in mind when you create new series from old is just how does the interval of convergence change? And the answer is it depends what you're doing. If you're substituting, then the new interval of convergence can be found by doing your substitution into the original interval of convergence. If you're multiplying and dividing two known series to create a new one, then the new interval of convergence will be the intersection or the overlap of the original intervals of convergence. And if you're creating new series through differentiation and integration, then the radius of convergence for the new series will be the same. Another way to say that is the interval of convergence is the same except the endpoint. So you need to check the endpoints. Let's look at examples of each of these. So we know from our studies this particular series, which if I write the first couple of terms out would be so, and that's equal to this on this interval of convergence. So what I want to do now is I want to use that known series and find the power series for this function. Well, what I'm doing going from this function to this function is replacing x with negative x. In other words, I'm doing a substitution. And so, just by doing my substitution above, which reduces to this, which I could generalize negative x to the k, which can also be written this way. Now in terms of my interval of convergence, I can just do the substitution I made into my interval of convergence to get the new interval of convergence. So replacing negative x there, multiplying everything through by negative 1 is going to give me this, which is the same thing I had originally. The absolute value of x is less than 1 is the new interval of convergence, in this case the same as the original. The next function I want a series for is ln 1 plus x. Well, I could get that if I integrate this function, that will become this. And so integrating this means I can integrate the series I just developed for 1 over 1 plus x. Now don't forget your constant of integration. Now you can find the constant of integration if you think about a particular value condition that you know. If we have this function, we know that f of 0 would be ln 1 would be 0. So if we plug in x equals 0 for all my x's here, I know that the output has to be 0, which therefore in this case means that c is 0. And therefore we're saying that ln of 1 plus x is this series, which I can generalize as follows. Now, the interval of convergence will be the same as the previous function that this came from, which is what I had above. But because I've integrated, I must check endpoints. So if x is equal to -1, I'm going to substitute -1 into my power series. This is going to mean the same thing as -1 over k, which I know it diverges since it's basically the harmonic series. So x equals -1 can't be included on the interval of convergence. Let's now check the other endpoint 1, plugging back into our series to get a series of constants. 1 to the k will be 1, so it'll just be that. And this will be the alternating harmonic series, which I know converges. So x equals 1 is included on the interval of convergence. Therefore, the interval of convergence not including -1, but including 1. Finally, let's do an example involving the multiplication of two known series to create a new series. Function f of x equals e to the x times cosine x. We know Maclaurin series for each of these, e to the x, which is this. X cubed over 3 factorial, which is that. 4 factorial, which is that. Over 5 factorial, which is this. Plus dot dot multiplied by cos, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, which would be 24, and on. I need up to degree 5 in my final series, so I have up to degree 5 in each of the factors. Now when I go to multiply out, I need to take all combinations of multiplication that are going to give me up to degree 5 terms. What I'm going to do is I'm going to multiply from the second factor. I'm going to need to multiply the 1 in the second factor to each of the terms shown in the first, because each of those will produce a term with degree 5. My second term, I'm only going to need to multiply this term by these 4 here, because the other two will give me powers greater than 5. And with this term, I will only need to multiply that by the first and the second terms here, because anything else will be degree 5 or higher. So that would be plus x to the 5th over 24 plus x to the 4th over 24. So if I now simplify this, I'm going to write this in increasing powers of x. I will have 1. Power 1 is only x. Power 2, those will cancel out. Degree 3, 1/6 minus 3/6 will be negative 2/6, which is negative 1/3, x to the 3, x to the 4. Common denominator is 24. 1/24 plus 1/24 minus 6/24 is negative 4/24, which is negative 1/6. And degree 5, 1/120th plus 5 1/20ths, which is 6 1/20ths, minus this one, 10 1/20ths, is negative 4 1/20ths, which is negative 1/30th, x to the 5th. There are the first 5 terms. For my new series, e to the x times cosine x. Since e to the x and cosine x have all real numbers in their interval of convergence, therefore the interval of convergence for the new series is all real numbers.